Hi guys. Okay, so now I'm starting a series of videos on organic chemistry. So in this very first video, we are going to look at the basic introduction to organic chemistry. So first of all, what do we know about carbon? Because organic chemistry is all about carbon. It's a carbon chemistry. So what do we know about carbon? We should know a few things from our previous courses, which is just very basic and general, and that is that carbon belongs to group 4A, right? So carbon, let's write this down. Carbon belongs to group 4A. That means it has 4 valence electrons and it can make 4 bonds. So this is a very basic things we learned in our previous, courses, Chem 1A and so forth. So how does that happen? So carbon, the atomic number of carbon, 6, right? This means it has got 6 protons, it has got 6 electrons, and its mass number is 12, right? So it can get the common carbon. So it is carbon 12. So that means the neutrons are also 6. So let's get this one here. 6 neutrons. 6 neutrons. The mass number of commonly known carbon, the more abundant carbon is, the mass number is 12 atomic mass units, and then it's also grams per mole. The more common one is the grams per mole, but you can also use atomic mass units. All right. Now, what is the electronic configuration of carbon? So it's 1s2, 2s2, 2p, 2, right? So how does it make 4 bonds when it has only, remember, what is bonding? Bonding is pairing of unpaired electrons. Bonding is pairing of unpaired. So let's look at it, what's happening here. Unpaired electrons. So what do we see here? So if you look at it, place this. Valence electrons. This is the, so here we see we have 2s2, right? And this is the 2p2. So I'm going to just put it as 2s, and this is 2p. 2p. And the electrons are 1, 2, and then the 2p2 right here. So when you look at the electronic configuration, there are only 2 unpaired electrons. So technically carbon should only be making 2 bonds, but carbon makes 4 bonds. That means it has 4 unpaired electrons. So where is that unpaired electron coming from? What happens is that one of the electrons from the s jumps. Remember the rule, half-filled and full-filled orbitals are more stable. Half-filled or fully filled orbitals are stable. So in order to attain stability, what is happening here? In order to attain stability, one of the electron, it jumps from the lower energy state to a higher energy state and comes here. And when that happens, we have new orbitals, and these are called hybridized orbitals. And that happens by mixing, okay? So these orbitals mix, the 2s and the 2p, all of the 3 of p's and the 1 of s, okay? These mix. And when they mix, now they have 1, 2, 3, 4. All of them at a lower energy state, lower than p, but a little bit higher than s. And now we have 4 unpaired electrons. So these are 4 unpaired electrons, and that makes carbon tetravalent. 4 unpaired electrons, and these electrons need pairing. So these are now sp3 hybridized. HYBR hybridized orbitals. Okay, and these hybridized orbitals have the same energy. So how do you show them? You basically show them. So here's carbon, and now you have one like that, like in a tetrahedral state. Okay, so one orbital at the back, one orbital in front, one orbital on the side, and one on the top, each containing one electron, that unpaired electron. Okay, so this sp3 hybridized orbitals makes carbon. How do you show them? You show them like this. So these are those 4 electrons that are unpaired and needing to be paired. So 4 unpaired electrons makes carbon tetravalent. Tetravalent. Okay, so this is how it happens with carbon. All right. Because of this, we have seen some of the examples, and those examples are examples carbon has been able to make, like examples are like we have seen commonly known CH4, right? CCl4, carbon tetrachloride, methane, these are commonly known. So these come through this single bonds. So they form like, so these are the structures, CH4, like that, H here, H here, and H here. And it can also form with chlorines. So this is the Lewis structure. So this is one chlorine, another chlorine, another chlorine, and another chlorine. So these can make single bonds. And so chlorines are, so let's just finish the Lewis structure of chlorine and carbons, 4 carbons. So this is the tetravalent state, making 4 single bonds. Okay, so this is one piece. Next is the so let me put some number parts here. So this is the first part, introduction to atom, so carbon. So this is one part. Next part is the second one, which is now not only the single bonds, carbon can also form multiple bonds. Okay, so multiple bonds are like in the first case, these were just, these are called a sigma bonds. And sigma bonds are what? These are the single bonds. Single bonds are also called sigma bonds. So 4 single bonds in both the case. But carbon can also form single bond, double bond, and triple bond. Okay, so single, double, and triple. So how does that happen? All right, or what examples are those? So let's look at some of the examples here in which carbon is making single, double, and triple bond still in that sp through sp2. So it goes further, hybridizations. So more hybridization, basically, let me write this down here. This is coming through the mixing of orbitals. So mixing of orbitals creates this. Mixing of orbitals. Okay, different types of mixing. So here we see 1 of S and all 3 of P's, they mix. And when they mix, they create sp3 hybridized orbitals, sp3 hybridized. Okay, but on the other hand, there is 1 of S and 1 of P can also mix, and that can create sp hybridization. Okay, sp hybridized orbitals. Next, when 1 of S and 2 of P's, 2 P's mix, then they create sp2 hybridized orbitals. So when I said when 1s and the 3 of P's mix, then they create sp3 hybridized orbitals. Okay, now sp and sp2, that can create double and triple bonds, right? So we see it depends upon the structure of the molecule and how. So So in that case, we will have the double and triple bond, so multiple bonds. So here, so this one is just a single bond. sp2 can make double, and sp3 can make, sp can make a triple bond. Okay, so this is beyond the course. So right now for Chem 30A, Chem 30B students, but just so you understand, right, that where that's coming from. It's good to know. So let's look at some of the examples now. Let's look at the examples like for example, let's see. Okay, let's look at this example. So we looked at when carbon makes 4 bonds. So that is, we already covered that one. That is, let's do some other, let's say Br with bromine, carbon tetrabromide, right? So that's one piece where 4 groups are on carbon. Next is we have carbon, this is 1 hydrogen, carbon, and 1 hydrogen here, and then double bond, carbon, and then you have 1 hydrogen and 1 hydrogen. Okay, so here there are, in the first case, we see there are 4 electron groups on carbon. Here, in this case, we have 3 electron groups of bonded atoms and non-bonded atoms, all those things on carbon. And now we have another scenario where we have hydrogen here, a carbon here, triple bond, and hydrogen. So in this case, what do we see? We see that there are 2 groups on carbon, okay, on either side. All right. So generally, we know a few things about carbon-carbon bonds. So carbon and carbon bonds, whether it's carbon-carbon single, carbon-carbon double, or carbon-carbon triple, regardless, these are considered to be non-polar. Now, even carbon-hydrogen bond is non-polar, okay? So whichever forms they are coming, these guys are, I mean, okay, it's the electronegativity difference between carbon. The electronegativity difference between carbon and hydrogen is 0.4. And in this case, the electronegativity difference in this case is, difference in electronegativity is 0. Right? So whether it's 0.4 or 0 to 0.4, that falls in the non-polar. Excuse me. So this is the non-polar bonds. Clear? So we see that these, when any time lots of carbon hydrogens are present, always non-polar. So this is one thing we know. So that's one thing with all these type of bonds. These are all non-polar. Even with carbon bromide, the net polarity is, it cancels out. Bromine is highly electronegative. So this becomes a non-polar molecule. This is a non-polar molecule. This is a non-polar molecule, right? So these are all non-polar molecules, overall, non-polar molecules. So anytime you have carbon-hydrogen bonds or carbon-carbon bonds, non-polar. But if there is oxygen, carbon is also known to mix with oxygen. So let's look at this one. So here you have carbon, okay, and it can combine with oxygen, bond with hydrogen, right? Carbon will always make 4 bonds. So that's how it's double bonded with oxygen and single bonded with 2 hydrogens. Or on the other hand, it can combine with something like this, chlorine on one side and 3 hydrogens on the other side. All right. So whenever there is more electronegativity, so we see that the electronegativity of oxygen is more than carbon. In this case, the electronegativity of chlorine is more than carbon. So where is the overall net polarity? Towards oxygen side. Let's make these. And here, the overall polarity is towards the chlorine side. So these are polar molecules. Overall, polar molecules. Although one side, these are non-polar ends, and this is the polar side, polar bond. Oxygen and carbon is a polar bond, right? So this is very important. You understand the basic functions, these characteristics or the properties of the bonds. Carbon-hydrogen bonds, as we said, are non-polar. So this is also a polar bond. So it's an unsymmetrical molecules, both of them. One side is polar, the other side is non-polar. So whichever side is polar, the polarity shifts that side, and the molecule becomes a polar molecule. Overall, net polarity is towards the one side. So there's something else I should put. This is delta negative, and carbon will have a delta positive charge. Here, carbon gets a delta positive charge. Chlorine gets a delta negative charge. Okay, so that's one thing. Another thing that we know about carbon now is that it can also form wherever these molecules, these organic compounds. So organic molecules are the ones that, carbon-based. Organic molecules, three-dimensional. They have the 3D shapes. Okay, so what are those 3D shapes? How do they look like? So they look like this. So you have carbon here, like a three-legged chair. So one end, like a wedge shape. So one end is towards you, pointing towards you. One leg of the chair is behind. One is on the side, and one is on the top. So like a three-legged chair, right? So that's one piece. So in 3 dimensions, you will see that's the shape in the 3D shape. We show like this. All right. So in this case, like 3-legged chair, like this. And so this is the seat, like that. Okay. So we will see the 3 dimensions. In 3 dimensions, pointing, this is also called a wedge shaped. This is the wedge shape of the bond. Okay, the wedge shaped bond. Okay. Now, this is the basic things. Now, another thing that we know about carbon, because carbon can make a number of, types of bonds, as we looked at it, that carbon can make single bond, double bond, triple bonds, right? That's one piece with carbon. Next thing, carbon can also make straight chains, right? The chains can be straight chain, and carbon can also form branch chains. These chains can also have branching, and branching can occur at different, carbons in the chain. So branching also can occur. Carbon can also form rings, right? And depending on what the deal is, carbon can also form a saturated. Saturated means all are single bond. Saturated molecules, that means saturated bonds. All are saturated bonds means that single bonds. All the bonds are single bonds. Okay, but carbon can also make unsaturated. Unsaturated means that there could be a mix and match of double bonds and triple bonds. That's why organic chemistry is so complex. We have about 18 million organic compounds are known. And still, more and more research is happening. So novel compounds are also being synthesized. So about 18 million organic compounds are known, and they have their properties have been understood, and we have synthesized many of them, or we have used them in the labs, or we have extracted them from the nature, right? From the plant kingdom, natural products, and many things. Okay, so then how do you manage all these? So what we do, we classify them. We classify these molecules into different categories. So we classify them, so these are the 18. So just to manage them, they are classified into families. And what are these families called? These families, just for the sake of, organizing these molecules, first of all, very broad families. And these families are based on functional groups. Functional groups. Okay. Now, these functional groups are the ones that react. Carbon-carbon single bond, carbon-carbon double bond, triple bond, and they may react, depends what it is, but mostly the functional groups are more active sites. So that's where the more active, this is the active sites generally. So we will study this more, but we are going to just keep it like this. In the next video, I'm going to make a video on all of the functional groups. Okay, now what does this mean when we talk about active sites? So look at this, different examples here. So look at this example of, okay, for example, you have carbon double bond, right? And this is one hydrogen this side. So this is carbon-carbon double bond. Now, you can, instead of having hydrogen can also be replaced with R. So it could be, R could be, any other thing that is non-reactive, or is not, we are not interested in the reactivity of that one. So this hydrogen can be replaced with R also. Like I said, R stands for rest of the molecule. That does not take part in the reaction. Rest of the molecule. Okay, so we don't have to write down all this excess thing, but we may only interested in the active site. So that active site is that functional group site. So here we see it is these two hydrogen. Now, two carbon. Now on this, when you add hydrogen, when this reacts with hydrogen, what happens? So here it's very interesting. This hydrogen attaches here. This hydrogen comes and attaches here. So then what is formed? Then a new molecule, hydrogen, and hydrogen, and a single bond. So one of the double bond breaks, because this is hydrogen is attaching. And so we have now, so this is a reaction with hydrogen. This is one example I'm giving you. And now you have a single bonded carbon-carbon, but totally different compound, new species. Okay. Now, as far as there is a double bond in a molecule, you will see the same reaction profile. So let's look at it another example. So here you have hydrogen and carbon, and you have another hydrogen here. You have carbon, hydrogen, carbon, and let's say put a double bond, hydrogen, and this is another hydrogen and carbon, and you have, let's say, here C, H, C, H, and H. So you see this, and it doesn't matter what else is there. But main thing here is that 4, 1, 2, 3, 4. Okay. So we see that this part, you can always, since this doesn't take part in a chemical reaction, this part can be shown as R. Okay, and since both the R's are the same, so this part can also be shown as R. So this is R. And you can call it, if they are different, then it's R1 and R2. But in this case, we have same story. Hydrogen will come. If you reacted with hydrogen, this would be the site where the hydrogen will hit. So we will have here one hydrogen coming and another hydrogen coming. So next, what is formed here in this reaction? So I'm going to just put it as R, C, hydrogen, hydrogen. The R, the rest of the part remains the same, but this part becomes a single bond. And you see, carbon still retains its, tetravalent. It's still 4. Whether it makes a double bond, and then like the 2 single bonds, or it makes 4 single bonds, or it makes like 1 triple bond and 1 single bond, it still all adds up to be 4. So 4 carbon is making 4 bonds in both the cases. But the hydrogen, when it attacks, it doesn't attack any other site, but only the part where there is a double bond. So this is no matter, what the functional groups are, those functional groups, as far as they have the same functional group, no matter what the other structure is, if it is non-reactive, it will be non-reactive, and we just call it R, rest of the molecule. Okay, so this is R, means rest of the molecule. This is important. Okay, so this is R, and this doesn't react. So we keep it like, like in the system, we only focus on the active sites. So this is the active site. In this case is the double bond. All right. Okay. Now we will look at the isomers later. Okay. So what else is there in this? This was a very basic introduction. Now we are going to look at the hydrocarbons. Okay. Now what are hydrocarbons? And then the representation. Okay. So 3, 4, and 5. Okay, 5. And 5 is about hydrocarbons. Okay, hydrocarbons. Now, hydro stands for hydrogen, right? And carbon stands for carbon. But remember, organic chemistry basically is of carbon and hydrogen bonds, and carbon and carbon bonds. But oxygen, nitrogen, sulfur, and all of the halogens like chlorine, bromine, right? Mostly chlorine and bromine are more common, but iodine and fluorine can also be found, right? Halogens. And then somewhere we also see phosphorus, but these are like commonly found, right? So these are like other molecules. So other molecules, somewhere. So commonly it's oxygen, nitrogen, these are more common. But anyway, so we will see these are organic molecules. They have this. So that is why these are hydrocarbons. Now, let's look at some of the very simple hydrocarbons. Simple hydrocarbons. Simple. Simple means, let's see, simple hydrocarbons. What are these simple hydrocarbons? 3 types: alkenes, 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 and alkynes. See, 3 broad categories. Okay, alkanes, alkenes, and alkynes. Okay, what are alkanes? Alkanes are the ones in which carbon and carbon is a single bond. Okay, carbon is a single bond. What are alkenes? Carbon double bonds, the ones that can contain carbon double bond. Alkynes, carbon triple bond. Okay, so that is present. Okay, so these are the very basic ones. Now, let's see some of the examples. Examples are, examples of carbon-carbon double bond is methane. Okay. You have heard about propane, C3H8. You've heard about butane, C4H10, all those gases in the labs, right? Protein, butane, so those things. Then this is the ripe fruit smell, the smell of the fruits, right? That is ethene, and that is C2H4, ethene. And then acetylene, that is used in welding, C2H2. Okay, so this is the, let me write this down, smell of fruits. And this is the acetylene. That's gas that's used for burning, for like, let me just do this here, smell of fruits. And this is ethene, E-T-H-E-N-E. And this is acetylene, right? And then this one, you know it, this is butane. And this is propane. And this one is methane. Okay, so these are the very basic hydrocarbons. Now, I'm not going to cover the properties of any of these, because properties kind of are easy. If you understand the hydrogen bonding, if you understand the, what is it called, the intermolecular forces, then, you know, properties are easy. All right, now let's look at the representation part. Okay, representation, how do you represent them? So here is the representation, REPRESENTATION, representation. How do you represent them, right? How do you represent them? So first example, let's look at one example of methane, simple one, CH4. Okay, CH4, methane, right? Lewis structure is hydrogen, carbon, hydrogen here, and then I'm going to make it like the actual, wait one second. I'm just compelled to do it, but okay, methane. The Lewis structure is simple, hydrogen on the top, and comes carbon, and then hydrogen, hydrogen, and hydrogen. So this is a simple Lewis structure. Okay. But you can also, when you do, this thing can also be shown as the space filling model. One second, let me just show it here, bring it here. So this is the Lewis structure. Now, this molecule, the space filling model, how do you show that? Now, in 3D, remember, it's in 3D. So we will have here, let's do this, carbon in the middle, right? And it's all space filling. So this is carbon. Now, outside the carbon, we will have this. This is one hydrogen. Sorry, let's get another one. So this is one hydrogen on the top. This is another hydrogen at the back, one hydrogen in front, right? And one hydrogen on the side. So more like this, right? So something like on those lines. So bigger one, because you can see it. So let's keep it like this. You're not able to see it. One on the top is the big one, and then the one on the side. So something on those lines. So this is also called this is the space filling model. Okay, the space, the ball and the space filling in 3D. Okay, now this is a simple molecule, but when we're doing like in drug discovery, there are certain software you use in 3 dimension, you can see, you know, how the molecule let's say a novel potent compound you made, how does this molecule like fit in the receptor region, right? The space inside the receptor region, how does it fit into that? So that's it. Now the ball and stick model is also the one that we commonly use, and that is, here is a carbon, you must have seen that, and you are going to see next is the next is a stick here, and this ball and stick shows us these are the hydrogens, and it shows us their angles, right? And so what are those angles? So this angle is 109. So here are the hydrogen atoms, hydrogens, each of the hydrogens are at this angle, and this helps us see the angle 109 degrees, right? And so that's the angle at which the hydrogen and the carbon, the middle one is the carbon, are, you know, located. So this is called the ball and stick model. Okay, so this is the ball and stick model. Okay, so we have this scenario. Next is we have another, the three ways we can show, and that is the wedge shape and the other one. So here is again carbon in the middle, and we will see the hydrogens at angle. So this is at the back, hydrogen, and this one is in the front, facing towards you. So we show it like that in 3 dimensions. So this is the wedge shape. Model. So you see all these different models. And then there are other types which are called the expanded. Okay, now the commonly used words, these are just, you know, for specialized, you know, for like apparatuses or for some special software, we use these. But commonly we use these: expanded, structural formula. Okay, now commonly used. Now the expanded structural formula helps us see the different, you know, angles. So in the expanded structural formula, we see, I'm going to just use one color. So carbon, hydrogen, and hydrogen, and hydrogen. And here we are not even looking at the angles. We just look at the different connections. So we see the connections of the, so these helps to see the connections of the atoms. That's it. Connections of atoms, whether it's a single bond, double bond, triple bond, how many are located where, you know, those things. So connections of the atoms are only seen. Very simple. Then sometimes, you know, this occupies a lot of space, the structural formula. So then we also use the condensed version, and the condensed version is the condensing of this. So condensed formula. And what is the condensed formula? The condensed formula is CH4. So condensed formula simply tells us that these are the like the combined, they break the bonds. So basically it just tells us the number of atoms, number of each atoms, number of individual atoms. But we do not know what their connectivity is. Connectivity only comes through the structural formula. But like I said, chemistry, hydrocarbon, it's all hydrogen, carbon, 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 hydrogen, hydrogen. So it takes a long of time. So we also have another type of formula, which is the line formula. Very commonly used is the line formula. And line formula is what? Now, we will have to assume now certain things here. For example, you are going to see the C2H6, for example, C2H6. Okay, let's say. So C2H6, carbon and carbon, that's the two carbons, hydrogens, one hydrogen here, one hydrogen here, one hydrogen here. And then here you have one hydrogen, you have one hydrogen, and you have one hydrogen. So this way, carbon is making 4 bonds, each carbon, and 6 hydrogens have been used up, right? So we will see this. So hydrogen can only make 1 bond, right? So this is the right structure, the Lewis structure. But how can you make this? Now, if you were to keep repeating this, so this is just going to be like one line, right? So this is so let's see this. This is the condensed version. One second. Let me make this a little more. Let me bring this here. Okay, so that we can see the line formulas a little bit more clearly. So this is the condensed version, right? This is the structural formula. Actually, this is not even the condensed. This is the condensed actually, but more like it's a molecular formula. So sorry about that. This is, you can write it condensed also, but this is more like a molecular formula. Molecular formula. This is molecular formula. This is the structural formula. Okay. And then comes the condensed formula. And we are going to write the line diagram or line formula or line. It's actually more commonly used as the diagram. Okay, so this is the line diagram of the same formula or line formula, either way, it doesn't matter. Okay, so here we see, in this case, it is CH3 and CH3. This is the condensed formula. Okay, and the line is this. Now, this means this is one carbon and this is the other carbon. And the hydrogens are basically, you know, all this are shown by the dot. So this is one carbon with the 3 hydrogens. This is another dot. So the dot represents the CH3. Okay, dot means the CH3, one single CH3. Okay, so I have drawn a dot, but once you start making these, then you don't have to, like, once you start making, then you don't, you know, you don't need to put the dots. All right, let's look at another example. So another example is C3H8. Okay, C3. So make 3 C's first. This is a simple structural formula. No angles, nothing. H8. Fill the rest of it with 8 hydrogens. 3. So we have all the 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, and 8. Right? So that's the structural. Now condensed. Condensed is CH3, this one. Then comes CH2, the second one, this one. And then comes the last one, CH3. This is the actual. So all the 3 carbons with the hydrogens have been placed. Okay. So how do you show the structure? So this is one end CH3, right? Then CH2, then CH3. So here, CH3, CH2, and CH3. Okay. So this is the way you will show this. Let's look at another one. So because this is important, let's look at this one. C4H10. Okay. C4H10. Sorry about this one. I'm going to use a different pen. C4H10. Okay. How does this come? C4H10. C4H10 is 1, 2, 3, 4. 4 carbons. Fill the rest with 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just put hydrogens. So all the hydrogens have been bonded, and all the carbons got bonded. Okay, so this is the structural formula. Okay, that's the structural formula. Next is the condensed. So remember the CH3, and this is the CH3. There are two CH2s in between, right? These are two CH2s. So 4 carbons. So in this, so how will you write this? This would be CH3, CH2, CH2, and CH3. So if you look at it, 1 carbon, 2nd carbon, 3rd carbon, and 4th carbon have been, placed. Now, how do you show this? 1, 2, 3, 4. Connect them. 1, 2, and 3. 3 bonds. Like actually, it's the CH3s are not written, right? It's just like the corners or the middle, folded part. So just keep this in mind that the end part is the CH3. And then the middle part is the CH2. The middle part in this case, so the end part is, well, let me put this in a different color actually. The middle ones, the middle, these ones, these are the CH2s. Okay, these ones. These are the CH2. Similarly here, this is the CH2 and this is the CH2 is right here. And the CH3s are in the corners, ends, and those are these ones. Okay, so this is how, these questions will be put up on the exam for the naming, for the writing the structural and the line and the condensed and all these formulas. Okay, so next in this video we are going to look at we talked about, so we won't be able to cover the isomerism in this video. So we talked about the representation, and then we are going to look at the nomenclature in the next video. Okay, the nomenclature in the next video, conformations, nomenclations, and there's a lot. But for now, we will just leave it at that. Okay. All right. So just practice this writing these formulas. All right. Thank you for watching. Bye-bye.